Okay,
Thanks.
so hello everybody. I'm Cristiano Capone. I work in INFN in Rome. So before starting, I really feel to say a special thank you to Paolo. Actually, without him, this work wouldn't even exist. I first met him 10 years ago when I started my master thesis. He was my supervisor, and I learned how to apply statistical inference on neural data with him. So for this reason and many others, thank you, Paolo. Okay. So let's start now. Okay, uh, to contextualize my contribution to this discussion, I would just like to make a quick memo of what Chiara presented yesterday. So basically, for the last couple of years, we have been playing with cortical simulations. So we try to build thalamocortical models, and we try, for example, to reproduce different cortical rhythms, for example, slow waves. And we always try to, of course, to take inspiration from data. So, for example, we know very well what should be the frequency of slow waves, of slow oscillations. So, for example, we can reproduce in this very simple model these nice oscillations, and over the course of sleep, you can see the frequency and the number of occurring oscillation getting the frequency getting lower and lower. And this was similar to what we discussed yesterday with Chiara Cirelli also. And then we also try to reproduce active awake dynamics. For example, this is during a classification task, still trying to give a look to distribution of firing rate in the different states and try to reproduce the correct distribution if compared to the data. And finally, we try to investigate the interaction between the two states, and we realized that actually the sleep could really be beneficial for the after sleep performances. We can see an increment of performances overnight, let's say, and this was allowed by down regulation of some of the synapses and up regulation of other specific synapses. And this was somehow related to better reorganization of the memories learned during the wake state. If you want further details on this, there are these two papers we published. Actually, the second paper is just accepted in post-computational biology. Chiara De Luca didn't tell you because this happened 1 hour after her talk, so I'm telling you. But so now the question is, can we redo all this in a better way? Can we redo all this with simulation which are not only data inspired, but which are data constrained? And with this, I mean, can we run simulation which are more realistic? And for example, also constrained, which are also brain specific, no? Constrained to the dynamics recorded from one single brain. And we are in this presentation, I will focus on this one step. If you can run data constraint simulations of sleep-like activity. So basically, what I will propose here is a method to infer from data the parameters of a model in order to run a data constraint model of the whole hemisphere of a mouse under anesthesia. In particular, I will show how to build a brain-specific simulation constrained to one specific to the recording of one specific individual. And finally, I want to point out that we are focusing on the spontaneous dynamics of the model, and these spontaneous dynamics should more reliably as possible reproduce the cortical slow waves dynamics observed in the experiments. Okay, so this is the data we are considering. This is a wide field calcium imaging from the whole hemisphere of a mouse. The mouse is under anesthesia and it's displaying slow waves propagation. Here you can see consecutive frames showing the propagation of these waves. We believe this kind of data set is really, really good for our purposes for building large-scale data constraint model for several reasons. First, the possibility to look at a very broad region of the brain, no? In this case, the whole hemisphere. Second point, the very high spatial resolution we can look at the data. And finally, and very, very important, the fact that the signal is only related to one specific class of neurons. In this case, it's only related to the activity of excitatory neurons. And this is very important when you want to constrain the activity of a dynamical model, of course. So there is just one drawback in the calcium imaging, which is the very long time scale of the calcium indicators. And you can see this in this very long tail here, for example. No? But actually, to fix this problem, we try to apply a temporal deconvolution to get a good proxy of the firing rate. And we get this deconvolved signal. This is the signal from one single pixel. And you can see that here is very, very more clear the transition from a down state and an up state. And here you can see how the data looks like before the deconvolution and after the deconvolution. And then you can see also in terms of spatial propagation after the convolution, the propagation of waves is much more clear. It's much more neat. Okay. So to be a bit more quantitative, we need to define a minimum set of observables to characterize waves propagation. And we choose as observables the local speed, which means the speed evaluated in each pixel of the field, the local frequencies, and the local directions. And basically, we consider 8 consecutive chunks, recording chunks from the same animal. Each chunk is a 40-second recording, and there is a break, a 10 minutes break between the consecutive recordings. And you can see reported here the distribution of the velocities for each recording, and the distribution is evaluated over all the waves and all the pixels of the frequencies and of the direction. Directions, I believe, is a very interesting observable. For example, you can see in this recording here, there is a measure, a most prominent direction of propagation in this direction here, while in other recordings, the direction are more, let's say, homogeneously distributed. And this is just to give you an idea of the final results. I hope you can see the movie. Can you see the movie?
Yes, we can see, yes.
Okay, great. And this is the original data, and this is the result of the simulation we get. Simulation is a mean field simulation, actually. And you can see that in the first place, simulation is displaying spontaneously slow oscillations. You can see that the frequency in a visual inspection is comparable to the frequency of the data, the direction of propagation of comparable, and so on. So now this is a sketch of the method we use. This is a 2 steps method, actually. And the first step is just a likelihood maximization, is a one flow of information from the data to the simulation, to the model. And we try by likelihood maximization to get an optimal estimation of the parameters. But then we also use a second step, which directly compares the outcome of the simulation to the dynamics of the data and try to further adjust parameters. And this is a sketch of the result, 3 consecutive frames of propagating wave in the simulations and in the data, and you can see the similarity in this wave propagation. Okay, so to give you a bit more details on the first step, basically in the very first place, we need to define the model. So each pixel is defined by a mean field population, and its activity at the following time is a function of the activity of the whole network at the previous time, and it's drawn from a Gaussian distribution. The average of this distribution is defined by a transfer function. This transfer function can be evaluated analytically through mean field theories. And this is a function, this transfer function in turn is a function of the inputs to the population. And the input to the population is a function of the parameters of the model. So for example, the connectivity, the external current, and the strength of adaptation. So from this, we can write the likelihood as the logarithm of this Gaussian distribution. And then we can try to, of course, the likelihood is a function of the activity, of the history we can observe from the data and of the parameters of the model. And we can try to maximize, to find the optimal parameters by maximizing the likelihood, for example, following the gradient, okay, of the likelihood. This is just a movie to give you an idea of the process of likelihood maximization. You can see the likelihood being maximized, and meanwhile the parameters bump out of the, you can see the final configuration of the parameters. So this is the special maps of the inferred parameters at the end of the likelihood maximization. And you can already see interesting things in the estimated parameters. For example, you can see regions where the parameters are higher, no? For example, the external current, no? But there is this region and this region where the current are higher, and they are likely related to the positions where the waves are most likely to be originated. And there are also an interesting correlation to observe. You can see here the strength of adaptation is higher in this region, but in this region is low, even though the external current is very high. And this can be maybe explained by the presence of a low level of recurrent connectivity. So you can see different regions with different configurations of the parameters. So, but now let's give a look to the outcome of the simulation of the spontaneous dynamics coming out of this model. Okay, and you can see this very regular oscillation from down to up state, down to up state. I think this is interesting to observe this in terms of a parameter space. You can see in this space there are different kind of states. A state where all the network has a high level of activity, a region where the network has a very low level of activity, and a region when slow oscillation are displayed. And you can see that this optimization method correctly places here the model in the region where the slow oscillation are present, are displayed by the network. However, if you directly compare, no, in a visual inspection, the dynamics to the original ones, you can see that the dynamics of the data is much more rich. Okay, it's much more irregular. If we want to generalize a bit, we can observe this in this space. Basically, we are considering the slow oscillation frequency and the direction. We can, for each of these observable, we can put a point in this space, and we can see that for experimental data, the distribution is much more broad, while for the simulation is much more narrow. It's almost all distributed in this region here. So the simulation is very regular. You can also see this by evaluating the entropy. The entropy of the simulation coming from this first step is much lower if compared to the entropy of the data. So how can we solve this? To solve this, we basically propose this second step. So what we do is we introduce a new ingredient, which is a periodic neuromodulation arriving to the network. And the parameters of this neuromodulation are the period and the amplitude of this periodic oscillatory current. Okay. And basically what we want to do, we run many simulations for different values of these parameters. So here you can see a grid search, a bidimensional grid search. And we try to make a direct comparison between the outcome of these simulations and the data. And we try to find the optimal values of the parameters, maximizing this similarity. And you can see there are points where the comparison here, the simulation are in green and the data is in orange. The comparison is very poor, while you can see points where the comparison is pretty good. For example, here, we identify this one as the optimal point. Of course, we consider also the other observables, the velocity and the frequency. And evaluating the KL divergence, we identify this point here, amplitude 3.5 at the period 1.5 seconds, as the optimal point. So now if we look at a direct comparison, we can see that now the simulation is much better. You can see the simulation is reproducing these doublets of waves, as we can see in the data. These very long, this longer, let's say, downstates, this dark vertical band, no? And this is something that is also present in the data, no? As you see. And also in terms of the Paro spectrum, the data and simulation are really comparable. Again, if we go in the parameter space, what is happening now is that the black point is a position of the outcome of the first step, while the neuromodulation, so the result of the second step, is moving the system along these two arrows. So when the system is moved in the right direction, basically the system is oscillating at a higher frequency. You can see the frequency color coded here. When the system is moved in this direction, you go in a region where the downstates are longer. And this is also reproducing this bimodality in the interwave interval, which is also observed in the data. Finally, if you want to give a look in this space, the outcome of the second step now is much more distributed and more similar to the experimental data. And in terms of entropy, now the entropy of the simulation is really not comparable to the data. And this is interesting, maybe to give a look how the entropy changes for the different values of the parameters, and indeed the optimal point we identified previously with the Kalbach-Leibler divergence is also a point where the entropy is very high. I don't know. I think I'm in time, right?
Yes, you have 3 minutes left to your 20 minutes.
Okay, thank you. So now, just to tell you that parameters can be inferred independently in the different chunks, in the different data sets. And this allows to, for example, to try to understand if the inferred parameters are consistent. And for example, if you look to the correlation between the connectivity parameters, the correlation is always between the correlation between the inferred connectivities is always positive. You can see the lower value here is 0.2, for example. And you can also try to understand which states are more similar than others. So for example, you can see very strong correlation in the input structure of T2 and T3 and of the T4 and T5. And you can give a look on how the average value of the external current, for example, changes over time. So you can also try to investigate how the parameters are affecting the dynamics in slightly different dynamical regimes. I want to mention that our formulation also allows very easily to use the same parameters we infer to run large-scale spiking simulation. And this is the match between the theory, the continuous line, and the simulations, which are the circle for the output firing rate of one single population. And here is the network behavior. So each pixel here is a population of 500 neurons. And you can see that just taking the same parameters we infer with the mean field model and putting them in the simulation, we're already observing nice propagating waves. Okay. So to conclude, basically we identified wide field calcium imaging as a very good, very valuable recording for large-scale data constraint modeling. Then I show you a two-step method to infer the parameters of a model in order to run a realistic simulation of the slow wave observed in the cortex of a mouse. Finally, I want to remark that this method allows to run brain-specific simulations of wave dynamics. So now I want to conclude with this sketch, and I would like to say that actually I think we did some work to fill this step here, and we would plan to keep going on with this plan. So does this make any sense at all? We believe yes. For example, we can ask whether the specific shape of wave propagation we observe in data can have a specific effect on the way memories are reorganized, the synaptic weights are changed. And also if, for example, the specific statistics of the waves in one specific individual maybe can have specific effects on memories. Finally, since I have I think 1 minute left, I would really like to point out one general problem. What we are doing here, we directly estimate the parameters from the data. Of course, this is not always enough. What is very important to do is to exploit the anatomical knowledge of the underlying system. For example, I think to what Chiara Cirelli discussed yesterday, to what happens to spines, or we should really use information about, for example, from the Atlas structural connectivity. For now, the main information about the main prior about anatomy we are putting in our model is that we constrain the cortical connectivity to exponentially decay with time, with the space. Sorry. Okay, so I think that's it. If you have any question, I will be really happy to discuss.